Okay, thank you. So my name is Colin Degraf. I'm a postdoc with Avishai Deckel at the Hebrew University. And I'm going to talk about work I've been doing with Avishai and with Jared Gaber and Frederic Bourneau, who are at CEA. Looking at stochastic processes within black hole accretion, the effects that has on their hosts. So I'll start a bit with some motivation, and then I'll get into how the impact that this Bursty accretion has on the black hole growth, and then on the host galaxy evolution. So to start with, I'm not really going to discuss details of the simulation model. All the simulations I'll talk about are done with the adaptive mesh refinement code RAMSES, and it uses a fairly typical model for black holes. So we have a sort of Bondi-like accretion and purely thermal feedback. It's isotropic, what's often used in a lot of these cosmological simulations. So the motivation for this is a set of high-resolution isolated galaxy simulations run by Jared Gaber and Frederic Bourneau. So here you can see the 6 simulations that they ran. On the upper 3 panels show the high gas fraction, and that's what we're interested in. And here you can see that the distribution of gas is very clumpy. You have very high density clumps which form through gravitational instabilities in the galaxy. If you consider what that does to the black hole, you start to see very strong effects. So here we're seeing the growth of the black hole in one of these simulations. And in the middle panel, you can see the actual mass growth. And you can see you have very strong jumps. So you're not getting a nice, smooth accretion history. You're definitely getting strong bursts. And if you look at where those bursts are coming from, they're coming from small-scale gas clouds on the order of 1 to 200 parsecs. So on the bottom, you're seeing the black hole accretion rate, and on the top, you're seeing the gas mass within certain radial scales. So you can see the low sort of blue and green curves there at the 1 to 200 parsec scale correlating extremely well with the burst in the black hole accretion rate. So the bulk of this black hole growth is all coming from these very high density clumps that are on the order of 1 to 200 parsecs. And we know from these simulations that they're also driving very strong outflows. So here's showing a set of time images from one of these simulations. And you can see when one of these bursts came in, it drives a very strong unipolar outflow. So the outflow is being driven just out of the plane. This is purely isotropic feedback, but we're getting very anisotropic effects just due to the local gas environment around. So it's clearly driving very, very high velocity outflows out of the plane. However, it doesn't have a big effect on star formation. So in the upper panel here, you can see strong outflow rates that are approaching the star formation rate. But if you compare the 2 dashed lines in black and gray, one of them has the AGN and the other does not. And in both cases, the star formation is minimally affected. So even though there are strong outflows being driven here by this Bursty accretion, it's not having a big effect on the star formation rate. And here's just a picture of one of these galaxies run with and without the AGN feedback. So morphologically, it looks very similar. And if you look at the total gas mass within the innermost region, this is within 5 kiloparsecs, the effect of the AGN seems fairly minimal. So from these isolated galaxy runs, we can see that resolving high-density gas clouds has a very important effect on the black hole's growth. And it has very strong outflows, but it does not appear to have much of an effect on the host galaxy. So what I'm then interested in is saying, okay, that's an isolated galaxy that was run for a relatively short time frame, didn't have any gas inflow, didn't have mergers, and the black hole only grew by about 20 or 30% of its total mass. I wanted to look at how that would be affected if we try and put this sort of model into a cosmological volume. So to get a sense of what this will mean, the cosmological run is going to have a lower resolution. So in black here is shown the black hole accretion rate from the isolated galaxy run with 6 parsec resolution, with no smoothing or anything. And in red is when we rerun the exact same simulation, but with 100 parsec resolution instead of 6. And you can see you miss out on all of the high accretion rate events because we're not resolving those 1 to 200 parsec clumps. So if you look at the total black hole mass growth, in red is the one at the 100 parsec resolution, the black hole simply isn't growing at all. So we're missing the bulk of these accretion events, which also means we're missing the bulk of the feedback that should be coming in. So to fix that in the cosmological run, we've implemented a stochastic subgrid model. So in blue here, I've just sort of highlighted one of these accretion events. So we calibrate the frequency that these high-density gas clumps should come in. They're on the order of 5 to 10 mega-year events. So we know that they should happen with frequency based on this isolated galaxy run. Using that, it's purely stochastic in the cosmological run, where we just, any given time step, it's possible for us to say we should have a gas clump coming in that we don't actually resolve. So we artificially increase the black hole's accretion rate. So when we do that, here's an example of one of the black hole growth curves. It's the typical sort of thing you would find in a cosmological run. Starts out with a strong sub-Eddington growth period. At some point, it turns into an extended Eddington growth phase, and then self-regulation kicks in and suppresses the growth. So if you look at how much of this mass growth comes from our stochastic clumpy accretion model versus how much of it comes from the smooth component in between those events, you see that the smooth component tends to be the bigger effect in these cosmological runs. But that's not really a fair comparison, because you need to keep in mind in the extended Eddington phase, the effect of a clump is irrelevant, because in the simulation we limit our accretion to Eddington. So what you really want to look at is what happens before this Eddington phase. And if you look there, you see that the amount of accreted matter comes about 50-50 between these short time scale clumpy accretion events and the rest of the time. And those short time scales have very big effects. So here's the same black hole, once run with the smooth accretion model in the bottom, and once run with our clumpy model. And you can see, by having small increases in mass very early on, you're able to reach the extended Eddington phase much faster. The black hole grows much quicker. In the end, you still suppress at approximately the same black hole mass when the self-regulation kicks in, but the history getting there is very different. So in terms of what that's going to do to the host galaxy, here you see on the left are the sort of standard smooth accretion model, and on the right is when you've included the clumpy stochastic model. So on the right you can see we have an evacuated region in the center of the galaxy where the feedback has really blown out the central part of the gas. And you can also see that the gas on the outer regions of the galaxy and sort of flowing onto the galaxy gets significantly disrupted and disturbed. If you look from same galaxy just from another perspective, you can see on the right-hand panel, the strong gas inflow has been completely stopped. It sort of hit a shock of strong outflowing gas, and it's not actually making it onto the galaxy. And from a third perspective, you can again see where the smooth model, you're still having strong gas inflow. With the clumpy accretion, that's really started to be suppressed and disrupted. So if you look at that same thing in the temperature scale, you can see with the clumpy accretion model, we are driving those similar unipolar outflows, just an inflating bubble in one direction out of the plane of the galaxy. So that's what's really causing all of these morphological effects, is driving these very strong gas outflows. So what we want to see is what exactly is happening to all of the gas here. So this is just showing you the amount of gas as a function of density and radial distance from the center of the galaxy, which is also where the black hole is located. So qualitatively, they're very similar in terms of the gas density, but there are differences. So one of the main differences is the clumpy accretion model, we've really blown away all of the low density gas. You can see it's sort of been knocked out to much larger radii and is actually outflowing. If you look at the temperature, you see something similar. At the larger radii, you still have the bulk of it is at moderate temperatures, but you do have several changes. So at the very small scales, you can see in the smooth accretion model, we still have quite a bit more cool gas, and we also actually have a fair amount of hot gas. Whereas in the clumpy accretion model, the cool gas near the black hole has all been heated up, and the fairly hot gas that's been there has actually been completely blown away. So this is where we're getting our two main effects. We're heating up the cooler gas, and we're really blowing out the hotter gas, which is also the less dense gas, as we saw before. So if we look at the density and temperature as a function of the radial velocity, here you can see they're very similar in the low velocity regions, but the clumpy accretion is able to drive very strong outflows, going up to a few thousand kilometers a second. and it's all the low-density gas. The high-density gas is not really being affected. It's not being driven out of the galaxy. And if you look at the temperature, you see that it's all of the high-velocity stuff is all coming from the hot gas. So this is all consistent with what Jared and Frederic had found in their isolated galaxy run, that this AGN is able to drive strong unipolar outflows, sometimes not unipolar, but always out of the plane, of the low-density, high-temperature gas. So if you look at what this is really doing for overall inflow and outflow, this is just a radial profile showing you the total gas inflow and the total gas outflow through spherical shells. So at the large scale, you can see the inflow in blue is fairly comparable. It's not quite the same, but it's pretty comparable. However, the outflow is dramatically different. So we're actually able to drive outflows 10 times stronger when we have this clumpy accretion model. There are sort of two other main features you can notice. One is in the clumpy accretion model, both inflow and outflow just sort of vanish at about 1 kiloparsec. That's because of this central region which has been evacuated of the gas. So once you've blown out that gas, there's really not any gas that's able to be driven as an outflow, and nothing coming in is able to survive past about 1 kiloparsec where it's reaching this hot gas. You also have this spike, which is not as interesting. That's this secondary smaller galaxy that's coming in. So that's not really relevant for the sake of looking at the AGN effect. So we know they're driving these strong outflows. To show exactly what's happening in terms of where these outflows are being driven, this is just showing you the velocity of the outflows, and inflows in fact, as a function of polar angle. So plus or minus 1 on the x-axis here represents purely out of the plane of the galaxy. So you can see the vast majority of the outflowing gas at 2 kiloparsecs is really coming from an out-of-plane direction. There's a little bit being flowing in and out at the relatively in-plane direction, but most of it's out of plane. As soon as you go to a larger radius, you completely lose the moderate velocity gas in the plane, and you're really only keeping the stuff that's strongly out of the plane. And as you go to larger and larger radii, this effect gets stronger and stronger. So you can look at all 4 of those together, and you can see the larger the radius you go to, the more strongly the outflows are directed purely out of the plane. Anything that tries to go even partly in the plane really doesn't survive. And if you compare this to what happens in the smooth accretion case, you just don't have any of the strong outflows whatsoever, as we would expect. So in terms of long-term effect of what this does, here you're seeing the cumulative gas outflow through a shell at 2 kiloparsecs. So the solid line is showing my clumpy model, and the dashed line is showing the smooth accretion. So you can see we're driving much stronger outflows at all times with this clumpy accretion model, which is what we would expect to find. Here, though, we're looking at the inflow, and so you can see until later times, the inflow is the same, whether you're talking about the smooth accretion or the clumpy accretion model. You just don't have enough feedback energy being blown out to do any of this. But once you get to later times, about when the black hole starts reaching a self-regulated phase, then you're actually able to start suppressing the inflow in this clumpy accretion model. So we're not only driving outflows, we're also able to start stopping the inflow of gas onto the black hole. If you consider what that's going to do for the star formation rate, you can see the solid line is the clumpy model and the dashed line is the smooth model. The clumpy feedback is able to strongly suppress the star formation in the host galaxy. This is not the same thing that was found in the isolated galaxies, where the star formation was entirely unaffected by this AGN. This is consistent with larger radii, so if we do the same figure just at 10 kiloparsecs instead of 2, we still see all the same effects. Outflow is always stronger with clumpy accretion. Inflow eventually gets suppressed, and the star formation is also suppressed there. So if you want to see sort of why the inflow is actually getting suppressed, here I've plotted a projection of the galaxy color-coded by the radial velocity, and I'm only showing you radial velocities from plus or minus 300 kilometers a second. So you can see in the clumpy model, out of the plane direction is much, much higher velocity than that. But if we look at where we're getting inflow velocities, then you start to see the interesting things. So in the clumpy accretion model, you have strong inflows. Same with the smooth model. The difference is the smooth model inflows have strong inflows in these sort of cold streams, and as you start getting further away from the central part of those streams, you still have weakly inflowing gas. The clumpy accretion model, you've taken your strong inflows and they're completely surrounded by very strong outflows. lost in its entirety the sort of low velocity envelope around these streams. So we're losing a lot of the inflowing gas that way just by stripping away all the lower density and lower velocity inflowing gas. And we can see that explicitly if we just look at the sky coverage. So how much of the sky do you need to encompass any given fraction of the total inflowing and outflowing gas? So in the case of the smooth accretion model, the inflow and outflow are relatively comparable to each other. If you compare that to the clumpy accretion model, there's a lot more distribution of the outflowing gas. And the inflowing gas is all being compressed into a very small volume. So it's not getting able to inflow except in the highest density regions that you have at the strong cold flows. And if you go to larger radii, you still see the same thing. The clumpy accretion has a much more widely distributed outflow, and that's compressing in the regions in which the inflows can survive, making it onto the halo. So in conclusion, what was found with isolated galaxies is it's very important to be able to resolve these gas clouds, these high-density gas clouds. In a cosmological volume, we can't do that, but we can implement it as a stochastic model. And we still find that it's very, very important for the black hole growth. Similar to the isolated galaxies, we find that it does drive strong outflows. Unlike the isolated galaxies, we found that it suppresses inflows, which didn't exist in the isolated galaxies, but also suppresses the star formation over the entire history. And that's very important to consider. And it seems that would be in conflict. It's actually fairly consistent with the isolated runs, simply because the only time we start to suppress star formation is after the black hole has been able to grow by an order of magnitude or more in mass. It has to have an extended Eddington phase, and it's only after you get that you're really able to do this suppression. The isolated galaxies only allowed black holes to grow on the order of 20%, and they were not in extended Eddington phases. So we expect when we run more isolated galaxies, but with larger black holes that are growing for extended Eddington phases, we'll start to see the same sort of suppression in star formation, and that's something still to be done. Thank you.
Questions? So part of the difference in your clumpy versus smooth is that you're just getting a lot more mass onto the black hole, a lot more feedback therefore. So if you had the same amount of feedback, would they really be so different?
So
what is it about the clumpy model that's making it have these very wide flowing?
There are a couple factors there. I've got a couple runs in the works that are trying to do a closer match for the black hole mass histories. But one of the things, just to clarify, in addition to a boost in the accretion, if you actually compare these, the low resolution run has a higher average accretion. It's hard to see in this figure, but if you actually decompose it.
You're looking at the log. Higher
right.
average, but only in the places where it's really low.
Right. So in the cosmological implementation, I've boosted the accretion when we have these clumps coming in, but it also gets suppressed when there isn't a clump there. So the total the total accretion rate should be fairly comparable for a fixed mass black hole over long time periods. Where you it depends on the object. Part of where it becomes problematic is you have things like this, where a small increase in mass in the black hole initially, because of the the accretion model in general scales like mass squared, it's sort of exponentially explodes in terms of a difference. So there are various comparisons we can do. So these are comparing at similar times. I've also looked at when the black holes reach similar masses, and the difference is not as extreme, but it's still clearly there.
Why?
When you have the clumpy accretion, you're having short periods of much higher feedback than you otherwise would have gotten. You're heating the gas up to a much higher temperature, so it's not able to cool quite as efficiently, and the outflows that it drives are at much higher velocities. So even if you're depositing the same total amount of energy, which you're not quite because of the difference in mass gains, but even if you did deposit the same total energy, the way you're depositing it makes it much easier to drive short-term, high-velocity outflows that really do escape the galaxy and impact the inflowing gas.
This will have an effect on the quasi-luminosity function.
Yes.
Really, one or the other is going to be favored when you actually compare to observations. Have you checked that?
No, because this is a zoom-in run, so I don't have the statistics for it. It's not going to be as problematic as you might expect, because what ends up happening, if you sort of look over here, if you didn't have, so here you can see these are the incoming clumps. If you didn't have those clumps, you'd still have variation here. It wouldn't reach quite the same highs, but it also doesn't go to the same lows.
Yeah, but you only detect the highs.
Yes.
Those low lows would be completely undetectable.
Yes, but what's happening out here is not really going to be detected no matter what. Where most, I mean, your luminance function is really detecting things more out here, and once you start getting into the extended Eddington phase, the clump won't actually have nearly the same boost. So you have a lot of sort of tunability in the model in terms of your exact seed parameter, which I didn't get into here. I can discuss with you after.
Other questions? David?
The inflow, at least one of the inflow mainstreams would likely be in the plane of the galaxy. I might expect that if you look at where the inflows might be detectable, there would in fact be an azimuthal tendency strongly in favor of in the plane inflow, while the outflow would be largely out. Is that consistent?
Yes. Yeah, yes, and I have figures I could show you later that's actually sort of theta phi distributions of both inflows and outflows. And it's very clear, in general, the inflow is predominantly in the plane, the outflows is mostly out of the plane.
It's not due to the thousands, but in fact due to the streams being in line with the perpendicular to the angular axis.
Yes, but it really depends on the radius you're looking at. So at the small scales, that is true. When you start going out to larger scales, there's no longer a very good alignment. So in terms of the feedback that I'm looking at, it's being deposited on the very small scales, and so that's certainly the case. But once you start getting out to larger scales, in fact, the direction of the incoming streams doesn't line up nearly that well with the plane. It's more sort of coming in and then flattens out, and then you have the plane here. So you sort of have this impact. I'm not sure if you're going to talk about that later. But okay, maybe. Okay.
We'll go with Daniel and Phil.
How massive are these galaxies?
They haven't gone. I don't have. This isn't at Redshift 4. This is mostly more at Redshift 6. But they're large, so it's sort of stellar masses of a little less than 10 to the 10. Well, I mean, at Redshift 6 and 7, they're pretty big. But yes, so we have. Correct. They're still forming stars, so it's not reached the fully quiescent phase, but it's having an effect on the star formation rates. And so some of the work looking at the lower redshift, sort of redshift 2 type of thing, is in the pipeline. But part of it is wanting more isolated galaxy runs, because at the moment we have a relatively small sample of the isolated galaxies with which to tune the frequency of these stochastic infalling clumps. And that's fine for what I've done so far, which is trying to see it does have a strong effect, and we do need to incorporate it better. But then for doing longer scale simulations, we want to run more isolated runs to give us a sense of exactly how much some of these parameters should vary with gas fraction or host galaxy mass.
Bill, Julie.
So the other thing I was going to say was you might want to push this as something that's more broadly applicable, not just focus on the aspect of accreting clumps, because there's lots of other things, not just 100 parsec size clumps falling in, that can lead to sort of bursty accretion on these scales from small
Yes.
scale dynamics and accretion is in the forest range.
Yes, so it's a stochastic model for accretion that can be applied for anything. So this was the initial motivation is this. There are a couple directions we can go. One thing is also breaking up, instead of having a single large clump come in, instead model it. If you had higher than 6 parsec resolution, then one of these 200 parsec clumps may be subdivided even more. So there are plans for doing a bunch of different tests on different levels of stochasticity and what kind of effects they can have.
Julian?
Yeah, just wondering if you try to push the resolution a bit further to see, to try to resolve some of these clumps and see at higher resolution if the stochastic model is the good description of what's going on.
No. I have limits on the runtime that I've been using so far. So we would like to do that and try one of these cosmological runs with probably not 6 parsecs, but pushing it down to sort of 25 parsec resolution or so, which may be sufficient to start resolving some of these clumps. And so once we have that, it'll give us a good sense. But part of the point here was seeing how much of an effect it does have. So at the moment, we're finding it's clearly having a strong effect. We do want to model this better. Now that we've shown that sort of evidenced with the resolution we have at the moment, we're going to try and push it in terms of improving the model and the resolution and see what we can get out of that.
Let me ask one quick question to change the subject slightly before break.
Sure.
This, I think, relates maybe to what Avishai is going to talk about later, maybe Kyle. So you show that it has this kind of pretty important morphological effect on the gas that's coming in, at least along the disk, that you get these more collimated inflows that align with the disk, and it really does affect that.
Yes.
Does that tend to suppress specific space and angular momentum for accreting gas? So that is, there's this sort of long-standing issue that you need to pick out the highest angular momentum tail of all the stuff that's coming in to give us disks in the long run that are as big as what we want. Does this kind of feedback actually suppress, are you actually picking out the angular momentum you want that's coming in as opposed to all the stuff that's coming in?
Well, and blowing out the low angle momentum theory.
Yeah. But I'm interested also in the stuff that's coming in. Because you want to be in the high specific angular momentum tail anyway.
So I haven't actually looked at that yet in these runs, but I think that it should. And I mean, the other thing is the effect on the inflow is measurable and rather relevant, but it's not stopping the bulk of the inflow. It's still a minority of the inflowing gas that's being stopped, and it's really only stopping the lower velocities in the the lower densities. So I don't think it's going to have a strong impact.
Lower
but
velocities is the low angular momentum.
yes, but so you're being left with the higher angular momentum that you would potentially want.
I can speculate on the answer to your question. We find that most of the angular momentum is in one dominant string out of a few. So this is the one that is probably unlikely to be disturbed per turn because it's more massive, there's more inflow, etc. So if I have to guess, I haven't measured this, it will not change much. The outcome maybe even increase than the specific, because
That's what I mean. That's
it
what I'm
will
thinking.
destroy the counter-rotating little streams.
Right. Yeah.
But you will have the most efficient feedback in the objects where you form bulges.
Yeah.
And you won't have the black holes on the feedback where you won't have formed.
Right, but more generally, if you have this.
Sort of it's just going the wrong direction. In terms of the objects, you basically where this is particularly efficient.
I mean, I think generally bipolar outflow of any kind, whether it comes from AGN feedback or not, probably going to have these kind of qualitative effects to suppress the inflow of the lowest angular momentum gas, and that's the gas we don't want.
Yeah.
I think. Anyway, okay, so we're going to break. We had a slight change of schedule here.